Good morning everyone, and welcome to today's worked exam answer video. Today I'm tackling another complex calculation. We're going to do a time of flight calculation, but this one involves two different ions. Now there's a couple of different approaches for how you can do this, and if you're more mathematically minded you're probably not going to want to do it the way that I'm going to explain. I, despite having an A-level in maths, do not find sort of making equations equal to each other and rearranging them is the most effective way of approaching a question like this. If it is for you, as I said on a previous video, that's absolutely fine, but I am going to approach this with a less mathematically minded head on, and try and show you how, yes, it might take you slightly longer to do it my way, but we're going to be using all the same skills that we would normally be using in a normal time of flight calculation. So hopefully that will reassure some of you that it can still be done without needing to be, a mathematician, quite simply. So I'll go through that and, like I say, explain every single step as clearly as I can, and read through the question with you. And then there was also a little tag on question at the end which I decided to leave in because it's quite a common one, and one that we do need to know how to answer using the correct terminology, which is about how the ions are detected. So we will answer that one as well. But yeah, I will do my annotations and I'll be back with you in a second. So let's dive into this question. So we've been told a sample of bromine was analysed in a time of flight mass spectrometer and found to contain two isotopes, 79 bromine and 81 bromine, and I've colour coded those in green and yellow throughout the question. After electron impact ionisation, all of the ions were accelerated to the same kinetic energy, and that is fundamental for how we're going to approach this question. And the ions then travelled through a flight tube that was 0.950 metres long. So that's going to be the distance that the ions are travelling through the flight tube. We are then told that the 79 Br plus ions took 6.69 times 10 to the minus 4 seconds to travel through the flight tube. So we have the time. We've been asked to then calculate the mass in kilograms of one ion of the 79 Br plus. We have to then finally calculate the time taken for the 81 Br plus ions to travel through the same flight tube. And then we're actually given two equations here, the kinetic energy equation, the velocity equation, and we're giving Avogadro's constant. So the information that's relevant to both ions I've coloured in blue. And as I said, the fact that these ions have the same kinetic energy is really important. So after ionisation, the next step is acceleration, and we accelerate the ions towards the start of the flight tube. Apologies for not being able to speak properly today. We accelerate the ions to the start of the flight tube by using a negatively charged plate, and at that point they all have the same kinetic energy. Why is that helpful? Because we can use the information that we have, so the time it took for the 79 bromide ion to travel through the flight tube to get the kinetic energy. Once we then have the kinetic energy, we can use that and the mass of the 81 ion to then work out the time that that ion took. And this is why some of you might be trying to set the half mv squared for each ion equal to each other because their kinetic energies are the same. That would work 100% as well. I just personally, like I say, from a non-mathematical sort of mindset, would prefer to do things this way, but that would also get you the same answer. Okay, so first thing I did was deal with the 79 Br ion. So the first thing I did was work out its mass. Now I've spoken about this in a previous question, but when we're working with mass in a time of flight calculation, we don't have the moles and we don't technically have the MR either. We do have the mass number of the isotope, which is 79, which I'm going to use in place of the MR. We don't have moles. However, moles is equivalent to the number of particles divided by Avogadro's constant, and we are asked to calculate the mass in kilograms of one ion. It'll always be one in any time of flight calculation because we're dealing with individual ions. So 1 divided by Avogadro's constant times by 79 gets us the mass in grams. And again, some of you won't want to write it. as 1 over this, and you'll put the 79 on top of the fraction. That's also fine. Some of you will also convert between grams and kilograms all in the same step. Also fine. Me personally, I find it much more helpful to see that that is representing my moles, the 1 over Avogadro's constant. I'm timesing that by the mass number, which is going to give me the mass in grams. And the exception for mass is time of flight calculations, where it needs to be in kilograms. And it does tell us that in the question, to be fair. So I've divided by 1,000 to get into kilograms. Then, using the time it takes for the 79 ion to travel down the flight tube and the length of the flight tube, I can then get the velocity for this ion, which came out as 1,420.0 meters per second. And then I have the information I need to calculate the kinetic energy. I've got the mass, I've got the velocity, so I can do a half times by the mass times by the velocity squared. And that gives me 1.32 times 10 to the minus 19 joules. And that kinetic energy is then the same for both ions. So then the ultimate goal is to work out the time it takes for the 81 ion to travel down the same flight tube. So we've got the kinetic energy now. So this is where it becomes much more like your normal time of flight calculation. So you calculate your mass of your 81 ion, again, 1 ion, Avogadro's constant, that's your moles, times by the mass number, gives us the mass in grams, divide by 1,000 to get the mass in kilograms. Then, because we've now got the kinetic energy and the mass, we can rearrange that to get velocity. So the first thing you would need to do is times your kinetic energy by 2 to get rid of the half, then divide through by the mass would give us velocity squared, then square root that would give us just the velocity. So then subbing in 2 lots of the kinetic energy we worked out before, dividing that by the mass that I just calculated, and that gives me a velocity of 1,401.0 meters per second. Now, just to compare that to the previous ion, because with questions like this, it would be a good way to see whether you were on track or not. The 81 ion is slightly heavier because it's got 2 extra neutrons, and therefore you would expect it to move more slowly down the flight tube, which is what the velocity is telling us. It covers fewer meters per second than the lighter one. So it's slower as it's heavier. Smiley face, that makes sense. When we then put that velocity and the length of the flight tube into the rearranged speed is distance over time, so time is distance over velocity, we then get a time that it takes for that ion to travel down the flight tube of 6.78 times 10 to the minus 4. And again, just to compare that to the time for the 79 ion, the 79 ion, which was lighter, moved more quickly, took less time to get down the flight tube. The heavier 81 ion took longer to get down the flight tube. So again, that seems like a legitimate answer. And if you got an answer that was smaller, so i.e. it took less time than the lighter one, hopefully you could then reason with that and go, that logically doesn't make any sense, and go back through your calculation and see where you may have gone wrong. If I was an examiner marking this, I would love this set out. It'd be so easy for me to go, right, they've done this, they've done that, they've got that value, they've done that, they've done that, they've got the answer, tick. Lovely. Had I have made a mistake with my final answer, it would be so easy to give me method marks. Now, I am not trying to suggest that this is the only way to approach this question or the only way that you should be laying out this question, not at all. But hopefully you can see how that would be very easy to award method marks to, and to find the final answer at the end, which obviously I wouldn't use colour in the exam, but I'd be underlining my final answer and making that really clear as well. Hopefully you can see why what I've done is a good example. Anything similar would be great, really great. Hopefully that makes sense. Any questions, as always, please let me know. And then to finish, we were given the question of explain how ions are detected and relative abundance is measured in a time of flight mass spectrometer. So other questions have asked in the past why we need to ionize the sample, and there's 2 reasons for that. One, when they're positive ions, they can be accelerated by a negatively charged plate, which gives all the ions the same kinetic energy, which is super important, as we've already discussed. The second reason is so that when the ions hit the detector, they can gain an electron. When the positive ions gain an electron, they become atoms again. Why is that helpful? because the size of the current that this generates, i.e. the size of the flow of the electrons to the detector, is proportional to the abundance of the ion. So if you have one ion hitting the detector, it will accept one electron, and that will be a minuscule current. Whereas if you have 1,000 ions hitting the detector, that's going to generate a current made from 1,000 electrons. So the size of the current gives us an indication as to how many ions are present. And that's the sort of wording that they would want you to use, that the size of the current is proportional to the abundance of the ion. Okay? As I've said, any questions, please do let me know, but hopefully that's been semi-useful to some of you. Anything that I can do to make things any clearer, do any similar questions to this, as always, please just let me know. Hope you have a really lovely day, everyone.